Let me introduce our next speakers. Dr. Matthew Pearce is a geophysicist with over 20 years' experience across the research, industry and government sectors. His current role at Geoscience Australia is as a senior advisor on geospatial standards, and through this role is a co-chair of the OGC Discrete Global Grid Systems Standards and Domain Working Groups. And he's the editor of the OGC Abstract Specification, Topic 21, for Discrete Global Grid Systems. And Matthew is joined by Robert Gibb, who has recently retired. I don't believe it, Robert. After a 35-year career as a geographic information researcher and innovator on the staff of Landcare Research here in New Zealand and its predecessors. His work on standards continues as a significant focus for his post-retirement activity as a research associate in informatics. He was a co-founder and co-chair of the OGC Standards Working Group on Discrete Global Grid Systems, which published the OGC Abstract Standard Topic 21 Discrete Global Grid Systems in August 2017. And now he's taking a role in bringing the standard into ISO TC 211. Please welcome Matthew and Robert. Thank you.
Thank you. Well, I'm going to start the talk and we'll do a bit of a tag team of moving backwards and forwards between, so we'll each blame the other if we go over time. Okay, so we are going to run through a sort of a quick synopsis of the journey we've taken to DGGS. So first of all, we'll present our own personal journeys that took us towards DGGS. These are not the only things that might lead you to DGGS, but gives you an idea of the diversity of where they came from. We'll then have a quick look at the standards process and of what DGGS actually is, following on that, and then a little bit about the future roadmap for DGGS and where that's going, some of the opportunities. So, what drew me to this? As you just heard, I've just completed 35 years at Landcare Research, and environmental sustainability, and that stretches the environment from Landcare Research's perspective, includes us as an integral part of that environment. And so environmental sustainability is not just the sustainability of what's out there, but the sustainability of society and everything we're doing impacting there. So everything we do collectively places excess pressure on the Earth and its systems. Climate change is the poster child of what that pressure is, but river pollution, biodiversity loss, and a whole raft of other things are all part and parcel of that pressure. Some of the changes there that arise out of that, we're 100% responsible for. River pollution would be an obvious one. Others are a complex mix of natural and human-induced change. Some of those are obvious, and some of them are elusive. Both individually and collectively, we need to take action. We need to participate. But in order to do that, we also need to be able to see the result, both locally and globally, of our individual and collective action, to give us encouragement to continue, because change isn't going to take place overnight. And one way that I see of doing that is that in extreme events, we need a real-time feedback loop that gives us an idea of what proportion of every event was our responsibility. And when I say real time, I put that in inverted commas because we can't do it as it happens in real time, literal real time in that sense. But there is a window of opportunity that follows each event where everybody is taking notice of it and everybody is very aware of it. That's the time frame in which we need to be able to respond. If we can come back with the answer in 3 months' time when everybody's forgotten about that one and the next cyclone is at the east coast or whatever, that's too late. So it needs to be in that window of opportunity maybe a few days typically, of providing that sort of feedback. So that's the perspective that I brought over a long period of time, of 35 years of doing the traditional sort of GIS and seeing the problems that it has in delivering that, that drew me towards the concepts of DGGS and started me working in there.
Goody. Okay, so my background's a little bit more diverse. So I started off my career 20 odd years ago in exploration geophysics, doing airborne magnetic, radiometric and electromagnetic surveys, from postage stamp sort of small surveys to large scale surveys that sort of for the national pre-competitive data. In that time, I experienced some of the opportunities and challenges of working with multiple types of data, multiple sources of data, different projections, what happens when you scale up from small to large, and that was really good, and that continued on into my my PhD, where I zoomed in on mine scale geophysics and sort of theoretical modelling, sort of getting into grids, funnily enough. When I joined Geoscience Australia, I joined actually as a seismologist, moving into global seismology for the Comprehensive Testban Treaty, and that brought its own set of challenges and a different set of data and different scales, moving from small to regional to global scales, and I kept seeing these recurring sort of glitches and issues sort of coming up, so since that time, a few years ago, I moved into the satellite Earth observation area in Geoscience Australia and headed up our contribution to a collaborative project called the Unlocking the Landsat Archive, which was around big data, getting the satellite Earth observation data off tape onto spinning disk, organised, integrated with high performance computing infrastructures to actually make it work. That was another sort of jump in scale, not so much spatially, but in volumes of data. And again, sort of grid thinking sort of became very much part of that. And one of the spin-off projects that came out of that for Geoscience Australia was the Australian Geoscience Data Cube, which is now sort of evolved into the Digital Earth Australia sort of program. And that's all around, well, slicing and dicing, how to tile and grid your data up to make it efficient to work with and analyse, so you can do continental analyses over a 30-year sort of archive in a matter of hours rather than years. And that's that was probably sort of governed by driven by my experience through my entire career, but particularly in the Earth observation space in GA, that we had a major problem of all of the work, or 80% of the work, in order to work with the data and to get outcomes, was wrangling the data, organising it, well, finding it, organising it, calibrating it, putting it in a frame that you can actually use, a sort of common framework, before you can even ask your scientific questions. And that was really the principle behind so the Data Cube and what's now the Digital Earth Australia. It's about taking all of that effort away from the front face, the scientists who really need to be able to ask and answer the questions and not have to deal with the data, the data formats and the organising underneath. That thinking is what really led to me to explore discrete global grid systems. So it was about that time I became aware of these global infrastructures that would allow you to scale up from local, very small areas to global, to be able to organise your data so that it can be worked with in an efficient framework. And at the time, this was about 4 years ago now, at the time there was no standardised way of doing this. There were many different approaches that people were doing that were all kind of similar, but each infrastructure was unable to work with the other. And so, and so with that, that sort of it creates barriers to interoperability, barriers to working and making asking some of the challenging questions around sort of what's happening with our Earth system today and sort of climate change problems. And that was where we went, right, okay, we need to fix this problem. We need to create a global standard that provides a framework for all of these different communities to maintain their particular flavour of operating, but to give them the tools to allow them to interoperate with other organisations and other communities. And that was the principle that we embarked on our journey through the OGC and discrete global grid systems, from an academic curiosity into something that's tangible and real. So as was said, the standard is the first standard has now been published earlier this year, and in that standard we actually define what it is to be a discrete global grid system. It's a spatial reference system that is a hierarchical tessellation or a grid of cells and to partition and address the globe. Now, not a flattened map representation, the surface of the globe, the curved surface. The DGGS as an infrastructure are characterised by their properties of cell structure, geo-encoding, so indexing and so forth, quantization strategies, getting data in and out, and the associated mathematical functions to traverse sort of within that environment. So they're more than just a grid protocol or that, they're an entire system, an ecosystem. So we, in doing that, I mean, we attempted to leverage off as many existing spatial standards that we could, and including sort of the ISO 19111, so the coordinates, looking at observations and measurements, feature geometries, and even simple features and the spatial relationships and DEM. The directionally extended 9 interoperability model. Basically, can you work out sort of where things are in space, but in a systematic way? And of course, metadata records of being able to sort of track, well, what is the additional information that goes with my observations? Can we need to make sure that tracks. And one of the things we found was, whilst we can link and hook into a bunch of these existing standards, which is great, means we've got a solid base to go on, there was a lot of subtle differences. There were a lot of terms that we used that is different when you apply it in DGGS. So we had to do a lot of redefining of terms and things, which is why it has taken us about a 3.5 year process to go from concept to a concrete standard. I won't bore you sort of and go into the nitty-gritty, but when you sort of pull these things, there is quite a lot to to building a DGGS, but the fundamental element of a DGGS is the grid cell. It's the atomic element, and it's the bucket that you put your data in, and it's the location. So now I'll switch over to Robert, and we'll keep moving.
So this slide is basically what is a DGGS on one slide. So what we fundamentally do is we start by choosing a solid with equal area faces, and we blow it out so that it sits on the surface of the globe. And then each of the faces of the original flat surfaced solid finish up as a patch on the surface of the Earth. And if you do it right, you can do it whether the surface you choose is either a sphere or an ellipsoid. And so you then have with a number of patches distributed around the globe that are all exactly equal area. And then you start tessellating each of those using exactly the same sort of algorithm, and you do that recursively many, many times. And there's 3 examples here, one where we're using squares, one we're using triangles, and one where we're using hexagons. Same principles apply to each. And for every cell we provide a unique index. And that unique index is a way of turning all of those cells into a single axis, effectively a single axis. It's not a traditional straight number line, but it is an axis that you can traverse through all of the cells of all resolutions. And that gives you a way of accessing really efficiently and for doing maths around surrounding cells and those sorts of things really efficiently. The cells constitute a fixed hierarchy, so we can see those top ones might be the first tier ones, the faces of the polyhedral. They might be the next one down, the next one down, but you can continue recursing that hierarchy as many times as you want to get down maybe to 10 centimetre or 1 centimetre or fractions of centimetre squares covering the whole globe. And it's that fixed arrangement, that repetitive fixed arrangement, that gives you an infrastructure that then lends itself to being massively scalable in terms of the analyses. And so that gives you access with very large quantities of data that you're likely to be dealing with, to be able to deploy them on the sort of cloud infrastructures and big data center infrastructures that are the character of today's computing. So what might this look like? If we take each of those and instead of looking at it from a global perspective, come down to a smaller area. So we've got here a group of squares put over a small part of Canberra. The next level down might be this size. So in this case, we're turning each square into a group of 3 by 3 squares. Turn each of those into a group of 3 by 3 squares, and here we've coloured the ones that more or less traverse a road and more or less traverse the boundary between the coast and the land. And you can do that again to give you a final level of precision again. So that just gives you a flavour for how that works if they were squares. But you can do exactly the same starting with triangles, splitting them 3 by 3. Same sort of patterning occur. The standard doesn't specify which of these to use. It's a framework in which you can choose whichever form of fundamental polygon you want to use. Or you can do it with hexagons. Hexagons don't overlap quite as exactly. They're not what we call perfectly nested, but there is nonetheless a way in which you can traverse those different scales just as well. So how do we now use this? And why would we want to do this? Well, how is this different from the traditional way of doing it? Traditionally, we've grown up with 2 dominant approaches to spatial analysis, referred to as the vector approach and the raster approach. So if we started to look at this scene, and I know it's a picture, I know it's actually a raster already, but just pretend that this is a piece of real world that we're going to vectorize and turn into part of a vector model. So if we were to vectorize it, we might pull this pair of features out of it: a road and parts of the lake. And what we would do is that each of those features we can then characterize. So in this instance, they have a feature ID, a unique feature ID. They have a type, one's lake, one's road. They have a feature name, and there may be a whole raft of other attributes that you would string onto each of those ones. So the road, you might, if you were a roading organisation, you might get, well, when was it last tar sealed? Is it tar sealed, or etc., etc.? What is the surface? All of those sorts of things. Or you might use it for navigation. So you might say, well, what's the capacity of the road? Where are there turning things, and all of those sorts of things. If we set off in the same direction from a rasterised approach, we finish up with a slightly different endpoint. We finish up with, here, part of it has been classified as a lake and is blue, and that's an individual pixel by pixel thing, simply saying that we think that that blue pixel is lake, that pixel there is red, and it constitutes a piece of road. This can be very efficient for processing many, many, many layers, but it doesn't have half the richness that there is in terms of the possibility of attribution that we've got on the vectorized side. So both ways have their distinct pros and cons. Sure, you can shoehorn in some of the other characteristics in either, but basically they are fundamentally different ways of doing things, each, as I say, with their pros and cons. Now, the interesting thing is that even if the operations are conceptually the same, the operational language and the algorithms that are used on each of these are different. So if you've learnt one set, you have to learn another set of operations to do the other ones. So not only is this two ways of encapsulating the data, it is two communities of different skill sets building up to use each. And so the cleavage between the two approaches is not just a technical cleavage, it is also a community cleavage. So if you bring something together which needs elements of both, what you essentially finish up doing is you take the element you need out of one and trying to bring it across to the other, so you can do some analysis that involves both. And as you can see, it doesn't matter which way you take this across. If I take a vector from one side and move it over to the other, or what you would like to be a vector but as a boundary, you finish up with a zigzag line that bears no relationship to the one if you'd done it directly from there. And if I go from the feature across to the raster side, I lose half my characteristics, unless I turn them into a whole lot of separate layers, one for each characteristic, which is quite messy, and you get all sorts of provenance issues. So, what's different about DGGS? How does DGGS manage to resolve this? So in the DGGS world, we take the idea of cells, and you've seen that those cells can be square or they can be triangles or whatever. We take the idea of cells, but we don't just have one resolution, we have the whole hierarchy of resolutions. So you can choose the resolution that is appropriate for the feature that you're bringing across. You can bring it across. And in a DGGS world, because every square has a unique ID, you can tag it with a traditional database style attached to it with all of the traditional features. So you're bringing the features of the world and the raster world together. Now you might say that the rasterized line is, it's still a nasty line in one sense, but if you really zoom in on a vector line, you'll find it's around all over the place. So there is a point at which the raster implementation of that is no worse than the vector. So where does this lead to us? So this means we have the equivalent of a DGGS point, the equivalent of the point in the vector world, we have a DGGS point. But this point is not just the point as in an XY or a latitude, longitude of two values on a real number line with many, many, many decimal points. You can choose the cell size that is appropriate. So that if I'm representing a power pole, you would choose a small cell size as a point. If I'm representing a house as a point, it would be a little bit larger. If it's Wellington, you would represent it as a much larger thing. So you can control, in bringing in a DGGS point, it also has a scale element about it. With DGGS vector, similarly, you can replace each of the nodes along the original vector with a cell, and the cell represents the uncertainty, the cell size, the uncertainty of the location. so that you're saying that this is carrying more information. Similarly with the polygons. But we can also do things like point clouds, LiDAR point clouds and this sort of thing, and tag clouds. Tag clouds, now we've got the little Twitter symbol there, but it could be almost any social media thing, or it could be a linked data environment like we were hearing about this morning and we'll be hearing about more this afternoon. Now, each of those things in the traditional way are yet another different way of storing things and yet another community of operations. So these would be 4 different communities, each with their own way of viewing things and their own way of doing processing. We can potentially bring them all together into the same infrastructure in doing it with DGGS. Back to Matt.
So we've just covered the raster vector divide and why and where DGGS is a really good platform and infrastructure to unify these things, but there needs to be more standardisation, and this is sort of what we included in the standard as well. So just to take a bit of a tangent here, with the into the shipping world. So back before standardised shipping containers, things were expensive to ship around the world, took a long time, things didn't quite fit on boats, and so there was a lot of things. And there's actually been some study by the World Trade Organization looking into what has been the impact of standardising on containers, on shapes, on these things over the economy over the last 20 years. And so what they've seen is that by standardising on a shipping container, there's been a 320% increase in the amount of bilateral trade over that first 5 years after they sort of embarked on that. But if you extend it over the 20 years, 790% increase in the amount of trade and sort of economic activity. And there's so you've got 45% sort of boost in trade and membership of the trade sort of agreement sort of committees and organisations of nearly 300%. And the whole sort of issue of globalisation has been enabled over the last 50 years it's been attributed to the implementation of a standardised shipping container, the ability to move things and that easily and in a standardised way has really enabled the world's economy. And being standardised, they fit seamlessly together. They allow for certain different sizes. So there are some. So if you can see there in that middle picture, there are different sizes of shipping container, and they're a standardised fraction of each other. But that allows that variability is a standardised variability, and because you can slap an identifier on each container. They're addressable, they're changeable, they're exchangeable, they're arrangeable. So you can do all of these things with shipping with shipping containers. But could you imagine what would happen if you tried to ship a container that was almost a standard size, but just say 10% different? And so you can imagine what would happen on the on that ship there. There'd be things sort of not quite fitting, things falling off the sides, and getting things on and off would be so much more difficult. And hence the challenges that the global trade had in the era before these came. Whoops, wrong way. And so if you stack them all up, what do you get? It looks kind of similar, doesn't it? It looks a bit like a grid. Looks like a standardised, regular grid-type framework. But standardising on and that's where we sort of we get to with the DGGS. But standardising on a shape, on a flat, nice, regular shape like that isn't enough, because we have a legacy. So we didn't have computers sort of decades and centuries ago when we wanted to understand the Earth and where we were, and so we worked out ways, going back to Da Vinci and Leonardo da Vinci and even further in some cases. We used the materials we had, so we worked out ways. How do we translate this ball onto a flat piece of paper that we can take with us? And so we have a legacy that has stayed with us around flat Earth thinking, flat Earth analytics, and working with the data, and that's still with us, unfortunately, today. So we have the Earth, we live on the Earth, we are on the soccer ball, and we measure everything on the soccer ball. But what do? We flatten it out, because that's the technologies that are at hand, and we know how to make a map out of it, make a flat map, and it's convenient, and it makes the mathematics seem easy. We can go straight lines. We don't have to worry about computing curves and things like that. Which, if you don't have access to a computer, yeah, that's a reasonable impost. But then we want to visualize it, and as we are moving from a local focused sort of world to a globally focused world, well, we want to visualize the globe. So why are we now that we've got the capacity to do it and tools, why are we still doing this? It's a question I leave to the floor. So here's an example of some of those challenges. So if we want to do some, and it's accentuated because we're dealing with sort of the polar region, but if we want to do an analysis, what's in the region or the area between Sydney, Wellington, and Davis Station? Intuitively, we want to say, well, what's the shortest line? So the geodesic line between these points, making a nice triangle of what we want to do. All right, but this it requires a fixed, scalable sort of approach. But when we try to do this in most GIS type tools at the moment, what happens under the hood? It might be visualised as round, but under the hood, everything's all flattened out. And so if that isn't, and so that makes the mathematics under the hood nice and easy. But if we're not careful about when we re-project it back onto the soccer ball, that's what we get. That's not what we want. We don't want to know about what's happening in that particular triangle. We want that. So that's an example of, well, we need to move. We do need to move away from this shackled sort of existence of round Earth, flat map, round visualization. And we have tools now available, including sort of especially through discrete global grid systems, to enable us to do that. And one of the key features that, like the shipping container, a DGGS is at each level is an equal area tessellation, but it's not an equal planar area. It's equal area on that globe. So we're actually taking a lot of that complexity out of the picture, and so that once you're in the DGGS, you can just play with index space, right? Index arrays, rather than having to work out these spatial things, and that can make a big difference to our ability to efficiently make decisions. So here's an example of how how you might use DGGS in action, and some of the challenges that we face with traditional sort of approaches. So if we look at, say, an area, okay, so we've got a very simple statistical area boundary here, a square, and we know that there's a bushfire impacting on that square. If that's the only information we have, well, that whole square, that whole region is being impacted by the fire. And through census information, we know that there are 65 people who live in that square. So therefore, there are 65 people at risk. But if we know that there is some water resources available, water mains, swimming pools, etc., we can say, oh, well, it's not so bad because there are 65 people at risk, but there's water. If we add in a complex sort of what that fire front is, well, it's not the same shape as the statistical area. It's some complicated fashion, and if we use a DGGS to represent that fashion, we're able and the various properties of that, we're able to take that complex picture of, well, sort of which bits fire, which bits not, and convert that to a one-dimensional array that allows us to very quickly, just based on index, sort of yes, no, yes, no, yes, no. And as a result of that, we have in this sort of crude example, 4 cells out of the 9 that have active fire on them, which means roughly 44%, only 44% of that statistical region is actually being impacted by that fire. If we step down and actually say, look, well, where are people living in this? And if we've got access to that demographic information, we can actually see a different pattern and at a different resolution as well. We can say, well, okay, so instead of 65 people as a blanket being impacted, we know, well, there's actually only 33 people that live in those areas that are being impacted. The rest are, well, you'd be concerned, but they're okay for the moment. And then if we look down at the water resources available, all right, which is another complex pattern, another data set, another resolution, we can pull that information out at a different layer in the DGGS, or a different level in the DGGS hierarchy, and get a sense of, well, which of these houses, which of these areas does actually have ready access to water. And from that we can make the assessment that, well, there might be 33 people impacted, but only 11 of them are at critical risk. They're the people that need to be triaged. We need the tankers there on hand because they don't have access to water. They need to be taken care of first. Then we can worry about the other 22 people, and then so on, so forth and so forth. So with the DGGS, we're able to move from these very coarse assessments of risk and impact that in reality are not very useful, to something that has a rich amount of information, and like Robert sort of said earlier, we need to be able to respond quickly to these things. It is efficient. We're using sort of simple array theory and array maths here, not complex vector calculations of sort of where is my house, which part of the polygon or the vector that it's in, how far away is it? We don't have to do that if we have access to a DGGS infrastructure. And so this is one of the drivers behind, well, sort of how do we bring this sort of social and this sort of statistical information together, and that's where DGGS as an integrator will allow us to unlock sort of new insights and data relationships that we had no way of really doing previously. And so we can start to bring in socio-economic data, environmental, geospatial data, move them out of their individual silos and into a place where they can actually be really useful. DGGS has potential to promote investment and capacity building, capability around the sharing and transfer of geospatial information, not necessarily by moving the data, but by moving the reference to the data. All right, so we move indexes, and because it's standardised and they're an interoperable sort of platform. We can have different styles, different cogs, but they will work together. And that's something that will foster inter-agency, inter-organisational collaboration. And so, and because of this recursion that is inbuilt into a DGGS, it allows us to easily scale from the very local to global without having to redefine everything at every step. And there's a lot of interest in this through the UN and the UN-GGIM, sort of around the Sustainable Development Goals. So DGGS presents as a very useful infrastructure that has the potential to allow us to properly measure how we're tracking on delivering on those Sustainable Development Goals. How do we measure them? Well, there is an infrastructure that could help that. And also supporting data sharing between these sort of institutions and various communities. I like to see sort of DGGS. I like to sort of refer to it often as it's an integrator. It's an infrastructure that sort of sits in the middle, and will allow us to pull communities together and sort of and to ask questions that we weren't able to do before. Not because it wasn't possible, just because it was hard. And that'll bring it to a close. Are there any questions?
Yeah, this is probably a pretty simple question, but I would be right in assuming that this would remove the 180-degree problem that we have on spanning the...
Yes. Mm-hmm.
Hello. How do you know from one system, so from one scale to one shape type, that you're working on and someone else can work to the same and use the same identifiers?
Just as infrastructure...
Yes, come back here.
Sorry. What we envisage is that just as infrastructure has developed around projections to be able to convert between different projections, that once this moves from an abstract standard, a theoretical standard at the moment, into a system where we start to have growth in these areas, that there will be those sorts of conversions available. So the question was, how do we, if you've got different families of DGGS that have been differently structured, how do we move between them? One of the things you may have noticed is that underlying all of those patterns are triangles. And so often you can disaggregate and recombine into neighbouring using common triangles sitting underneath there. So it's not quite as bad as you might fear, shall we say. But we also would expect communities to arise that have agreed, just like New Zealand has agreed on NZTM, some people might still be using NZGM, but basically we've settled on NZTM. We expect things to settle on particular DGGS for particular styles of things.
Hi, would you consider the hexagon a less suitable shape in that if you're moving from the smaller scale up, you have multiple parents?
Well, no. Well, it depends. Yes, you do have multiple parents, particularly on the crossing cells, but that arrangement is a fixed function of that hierarchy. And so there are ways you can get around that, but in a standardised way. But actually, from my discussions with a lot of statistics people, hexagons actually presents as a much nicer way to deal with spatial associations than other styles, because for each hexagon, the centre of that hexagon is exactly the same distance from the centre of all of its neighbours, regardless of what sort of direction you're pointing in. Whereas if you look at a square, when you sort of east, west, and north, south is the same, but on the diagonal, that's a different area. Which for statistics, that can be like a complication that you need to deal with. The other thing too is, well, it's not just with hexagons. Sort of, it's true with all flavours of DGGS. Is depending on how you define your refinement sort of mechanism, you can get sort of blocky sort of steps between your resolutions, or you can get smooth steps between your resolution. And so it starts to come down to choices of your use case. Which style or flavour of DGGS do we feel is best for our application? And like Robert said, is that with the standard underpinning these, there are mechanisms that will allow you to translate between the different flavours of DGGS, but in a consistent fashion.
I'm sorry, I'm going to have to intervene because we'll run out of time. This is such an, I think, and carrying on with questions for this, but I am discussion time later this afternoon. Could I ask Marcus that you or hold those questions and also come back to our speakers in the break, so that we can just keep on our schedule here. I wish to thank Matthew and Robert very much, because this is exactly what we were seeking, an insight to this new way.
Thank you.